All right, couple last days to wrap up here. We had just finished up Eulers and we were doing our homogeneous solving of equations. Now we want to look at non-homogeneous, and this has the same methods, all right, the same two approaches that we had when we looked at these for second order, all right, undetermined coefficients, all right, and then variation of parameters. This, all right, again, extends. We have the complementary and the particular solution. This extends directly from what we did, right, in chapter 4. Notice, all right, find the general solution. Do not solve for the constants. The directions are the same as well, which means we need to focus on making sure we understand what the functions look like. So, all right, we solve the associated. Just to refresh on how we approach these. So we solve the associated homogeneous function, right? Which means then we solve the characteristic equation. We have our Wolfram. It's going to help us do the factoring. Actually, this one we could have done with synthetic division, if we had the desire. Right, just because the real solution is 4. You guys remember basically at all how to do that?
Not at all.
You do like, you put the 4 here and then drop that term down and then multiply it. You guys remember that at all?
No, sir.
No, let's take a quick fun tangent here. I remember doing it. Process I don't exactly remember. Okay, we're gonna use Wolfram, but just to refresh, if in case you need to help someone else. So with synthetic, okay, so we would have found that the solution was R equals 4, right? Just by graph, right? We would have graphed and found this guy.
Okay, so we have to use technology in some way.
Yes.
Or you by hand plot the points.
Okay, well, yeah, you can guess and check this. But no, I was like, you can also do that one where it's like that. What it's called? You take the first term and the last term and all the multiples. I don't even remember what it's called. This is horrible. You graph it, you find 1. And basically what that would have given you is this gave you 1 solution, right? But that's all that shows up on the graph, R equals 4. Then you do synthetic, taking just our terms, well, 48, negative 64. So synthetic division looks like this. So the first one is you drop that term down, then you multiply. So 4 times 1, right? And basically the sum is the down, multiply as the diagonal. 4 times 1 is 4. Do it again.
Negative 48.
Negative 8. Right?
Okay, so it's add and subtraction up and down, crisscross applesauce as the multiplication.
Yep.
Okay.
And then multiply, and now we have negative 32. And now sum that, 16, multiply again.
By 8.
By 4.
By 4.
It's always this guy. Multiplying this guy.
Okay, so 64.
Yep. And oh, look.
It works out to be 0.
It works out to be 0, and this is r squared minus 8r plus 16. And that is a perfect square trinomial, which factors r minus 4. Want to be squared. And look. So, and then the solutions would be r equals 4 multiplicity 3. Just an FYI.
Sweet.
Okay, so R equals 4. Equals 3. The thing is you can only do that if you have it nice. Or a either super simple fraction or like, because even once it gets like 12 thirds or 12 like fifths, let's call it 12 fifths. That's already sucky to do this, right? Like, because you have point, I mean, what was that, 0.4, right? 2.4. Like, yeah, to do this, to do synthetic division with a decimal is like
Miserable.
really. Okay. Okay, so we got that. All right, so the complementary solution. All right, if I have R equals 4 multiplicity of 3, what's the complementary solution?
C1 equal T E4 T squared E4 T.
Good job. Same thing we did before, extended. All right, now let's our G of T function and see if we can identify a particular guess, right? We've had lots of practice at this now, so we should be awesome, right?
Sure.
Okay. For my guess, what should I do?
For 12, would that just be constant?
Mhm.
Just A. So A minus B to negative.
This back to your quiz. No minus. It's all plus. Because by definition, a constant, what's the sign of this? Whatever I want it to be. So always pluses. Okay. Okay. All right.
So it'd just be plus B e to the negative AT. Plus 2 4T.
Plus what?
2 or C e to the 4T.
Absolutely. 100%. That's what I would start my guess with. Okay, pluses.
Pluses.
Because by definition, a constant, why you have signs messing in there when you have to start multiplying things through, the negative actually would make your work. Okay, important. And it's important to understand this part. It is saving us a ton of work. But that means we have to create the correct guess, right? We're not solving for it, but it means all the thought we're doing, right? Because if you go to solve it and you have a bunch of negatives, you just triple, because now you have to keep track of all those signs and it's a nightmare, right? Never make it harder on yourself. Okay. Okay, so that seems like a good guess. Now recall, with your particular, once I have my guess, I look back at the complementary and I say, do all functions have distinct coefficients?
No.
No. Specifically where do I see a problem?
C e to the 4T.
Right here, C e to the 4t. Oh, so in order to get rid of that, multiply that by t and solves it? No, why not?
Actually, that's the complement.
Oh, because then it matches this guy. Okay, so t squared. Oh, almost. One more. D cubed. And really, that's it. And, all right, do I need to multiply the whole function?
No. Yes. No.
Just that piece, right?
Just, I was like, he said no, and I was, and then he's, yeah, I was about to write, I was like, yeah. Thank you. Let's say adjusted. Just. Yes. All right, so. Y of t equals C1 e of t. All right, beautiful. Let's do that again. All right, this time we're going to find the constants because I want to show something. So once again, all right, I have a homogeneous equation.
associated. And this one, actually I can't solve that. Technically, that's correct, but since I already solved this. I think it goes that way.
And then C1 e to the 0t just
Becomes C1.
all right. So for our particular guess, all right, our function is g of t equals t, which means then what should we guess for our particular?
GT plus B. Maybe.
Yeah, I just want I make sure the constant's so mine. I was like, because so you could say a plus bt, say, right?
Oh.
I was like just making sure it was like my constant's lined up. Okay, and then does that look good? That's appropriate for the guess. We have to compare that to
The homogeneous.
the homogeneous, the complementary. So does that look okay?
Seems like it.
But the B screw things up?
Yes, the B screws things up because it's the same as what?
C1.
C1. Okay. All right. So that is important. This is the function next to it is what? What's this function?
Constant.
One, right? I mean, what's the function next to this? One, which means that I have a function next to a constant, which is not distinct. And then what do we need to do then?
Multiply everything by t.
Yes, this one, do I multiply just the b by t? All right. Okay, once we have that, solving for the constants. We have our particular function. Again, we haven't done this in a while. So we take the derivatives. And this is where solving for the constants gets even worse because, right, we have to do this multiple times. And we plug those in.
into the original differential equation. Good news, this actually solves pretty simply, which is why we're doing this. Those equations are about as easy to solve as they come, right? Which means, all right, I found, all right, my coefficients for A and B. Now, be aware, this doesn't help. Were we doing an IVP here? No. So we're solving for the constants, but we're still leaving this as a general solution. So, all right, I have my A term, which is -1/2, and my B term is 0. Oh, look, that goes away. Which gives us our finished solution. All right, I want to show that because our other method, variation of parameters. All right, we saw with variation of parameters, unlike undetermined coefficients, okay, this can solve anything. All right, it's just about how difficult that integral is. The other nice thing is that this solves the problems that undetermined coefficients suffer from. That is, undetermined coefficients is really only good for 3 functions. What 3 functions?
Sine, cosine, e.
Okay.
Oh.
Sine and cosine is 1 function. Sine, cosine, e.
And just t to the power.
Polynomial, right? Yeah, exactly, literally what we just did, right? So if you have anything else, okay, then we need to use variation of parameters. We get to use back to our wonderful Wronskian. Once again, just like everything in higher order, this is why this is the best section, because it's everything we've talked about with the most natural extensions that can exist. So many things don't have nice, easy, natural extensions to higher order. Differential equations, almost every technique we've talked about does, which means that's why we spent, right, 85% of the class doing all the low order, because it's all the same, right? Literally everything we're doing now, it should just be review. Okay. Okay, so the Wronskian wonderfully extends, as does, if you recall, we found the individual Wronskians to solve, all right, for our particular numerators in the variation parameter functions. And so notice the equation for the particular function for variation parameters has an absolute perfectly natural extension, all right, as we continue. Since we're doing a bunch of Wronskians, all right, that is a bunch of determinants, all right, it is helpful to use Wolfram, and I have the code that I used for this one, but it is exactly just doing determinants. All right, we'll write it out, and then I was like, I'm not even going to plug it in because you can see it when you plug it in. All right, so using various parameters, I want to find the general solution of the differential equation. Oh, look, the one we just solved. All right, and so note we already found the complementary solution. All right, C1 plus C2 ET. Which means, all right, then we can use variation of parameters to find this technique as well. So I'm calling my functions And again, which one you actually call 1, 2, and 3 doesn't matter. So, all right, we make the overall Wronskian. That's our functions. And then their derivatives. And this, right? While this determinant is not overly hard, because technically, right, was what we talked about before. If I was to do it by hand, how much do I actually have to calculate? Look, 1, all right, and determinant of that wouldn't be expected. Okay. However, doesn't always work out so nice, which is why I have the code up there. It actually comes out to 2. All right, then each of the individuals. All right, so Wronskian 1. So recall what this is. Okay, this is exactly what we did. With Kramer's rule back in chapter 4. 1 indicates the first column. In the first column, I replace that first column with all zeros and a 1. So just kind of coincidentally turn that upside down. Otherwise, these remain. This is also, so with Wolfram, right? So how you can actually say Wolf, like do the Wronskian. You can't say do the Wronskian 1, right? It doesn't quite understand that, right? Which is why I have that determinant code there. So you can say Wronskian, do the Wronskian for this top one, right? But otherwise, when you find the individual pieces, same thing. So now what should this one look like?
Your second row is 0, 1, 0.
Yeah, so what's the first column?
0, 0.
Yeah, so it's back to 1, 0, 0. Then this becomes 0, 0, 1. And this is e to the negative t, negative e, negative t, e, negative t. Right? And then lastly, so again, creating those, not too difficult. And then these ones, like we could do by hand, but again, Wolfram Alpha is there to help us out. Our whole goal is doing the particular. So in 3 dimensions, it would look like this. So, all right, we found, right, and that's why I identified all that as we went. We have G of T, Y1, Y2, Y3, the Wronskian, W1, W2, W3. And then just a matter of plugging in and hoping these are easy enough to evaluate. Because that's the problem with variation of parameters. They can get challenging. Now, good news, that was like we knew our function was T and something like that, so it wasn't overly complicated to start with. simplifies down actually pretty nicely. First integral piece of cake, t squared over 2. What about the second two?
By parts.
Ah, our favorite method by parts. Okay. Nothing to those. After some multiplying out, it actually solves down pretty wonderfully here.
Okay. Here. Did we get the?
The answer's different.
Ah, excellent. I was like getting ready. So we get that. Now compare to. Right, what we got with undetermined coefficients.
It's been shifted.
That's what we got with undetermined coefficients. Here's what we just got with variation parameter. How is this different?
They're off by 1.
Yeah. Can I account for that anywhere?
C1.
Ah, well done.
That's just a constant. This constant, when we go through and would solve the IVP, this constant would be
1 more.
one less.
One less, okay.
One more, one less. One or the other. It doesn't really matter. All right. This is off, right? This C1 is equivalent to that C1 minus 1.
Yeah, so it'll be one more, right?
I think I'm like I'm like what?
Because yeah, because if this is 5, 5 minus 1 makes this 4. Oh, this is less. Yeah, okay. I don't know why we're overthinking that. Okay, so the idea is that these are the same. Okay,
The whole idea is what the constants represent, right? Just end up slightly off, but it does end up with the same answer. But this is very, very common. If this solution had an e to the t in there, it's because they're accounting for something else in there too, right? So you see that shift quite a bit. This is also why we like distinct constants, because you don't want to solve something and end up with, I mean, I could break this C1 into 10 numbers, but you want to have to solve for 10 more additional constants. That's the whole thing. All right. So, all right, very, 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 very fun stuff. Look at one more of these, and going back to our beautiful Cauchy-Euler equations. One last chance to look at Euler, all right, to appreciate it.
we saw these also in chapter 4, section 4. That remember that if we
Don't have, right, a nice quadratic type, or now quadratic or higher level type equation, all right, with constant coefficients, all right, we have to be given, all right, the solutions to the differential equation. But we can still solve this down in order to find what we're looking for. Remember that form is still everything. And in order to use, all right, variation of parameters, just like we had in section 4, we didn't have to emphasize it very much right here. But everything with the form of variation of parameters, the function, all right, the value in front of the highest differential has to be a 1. Which means all I have to do with this guy is going to take this whole thing, divide that by x cubed. That adjusts our g of t, which will matter, or g of x now. Okay, so y1, I'm going to call x, y2. And now our g of x is 2x. If you don't make that adjustment, right, we would have ended up with 2x to the fourth, and this wouldn't have worked. The only important part with variation of parameters, right, is that that coefficient in front of the highest order has to be 1. And then we can do the Wronskian. Let's take some derivatives. And again, doing the Wronskians is where Wolfram really, like, okay, we could do it by hand, but Wolfram is very helpful here. Once we have all our pieces, and again, now variation of parameters just really becomes about making sure you have everything organized, you have everything identified, all right? Plugging in and then making sure that that integral is able to be evaluated. And then about as easy integrals as we actually could end up with, nothing but reverse power rule here. Which simplifies down just beautifully. Which simplifies down. All right. We had our functions y1, y2, and y3. All right, so we already had our complementary solution, which we could have identified immediately. And then simplifies down. All right, that's all I want to do today. We'll finish up the last little bit, all right, of lecture next class.
You on Tuesday?
Next lecture class.
Yeah, okay.